April 4th, 2024. A Tuesday afternoon in downtown Fort Lauderdale, where the laws of physics suddenly overruled a $150 million construction project. At 4:30, dashcam footage captured a blue shadow engulfing a Tesla on the Southeast 3rd Avenue bridge. A massive section of a tower crane, weighing several metric tons, slammed into the asphalt, killing 27-year-old rigger Jorge De La Torre as he fell 91 meters to the bridge deck. This wasn't a crane tipping over in a storm. It was a surgical mechanical failure during a jump. But why did the structure fail during its most vulnerable moment? And how did a routine procedure turn into a $100 million catastrophe? To understand the carnage, we have to look inside the dead zone of the climbing frame. In the world of high-rise construction, we talk a lot about zero tolerance for error. But the Fort Lauderdale incident reveals a haunting gap in site safety culture. There were two riggers working inside that mass section when it began its descent. One rigger survived because his lanyard was properly anchored to a structural point. Jorge De La Torre, however, was not connected. For the industry veterans watching, this is the ultimate red flag. It suggests that the pressure of project deadlines might have compromised the very protocols designed to keep workers alive. We have to ask, why would an experienced crew be working in a section that wasn't mechanically sound? On most professional sites, a jump is preceded by a rigorous checklist where every pin, weld, and cable is verified. Yet on this project, something fundamental was overlooked. The industry relies on qualified persons to sign off on these maneuvers, but when that person is also under pressure to keep the project on schedule, the objectivity of the inspection can vanish. This introduces an industrial tension that no safety manual can account for. Was this an isolated mistake, or is there a systemic problem with how we verify safety during a crane's most critical phase? When we look at the rigger's fall, we aren't just looking at the failure of a lanyard. We are looking at the failure of the entire safety hierarchy that allowed that section to move while men were unsecured inside it. To understand why that section fell, we must perform a deep dive into the jacking frame, also known as the climbing frame. A tower crane doesn't just sit there, it must lift its own head to grow. The climbing frame is a large, four-sided steel sleeve that surrounds the mast. Using massive hydraulic jacks, this frame lifts the entire top assembly, the jib, the counterjib, and the cab, just high enough to create a gap in the mast structure. This is the only moment the crane's main structure is disconnected from itself. For a few critical minutes, the machine is held up only by support pins and hydraulic pressure. On April 4th, 2024, the crew was stepping the crane, sliding a new section into that void. Investigators from the Occupational Safety and Health Administration, or OSHA, found that a support cable within this climbing frame snapped. This cable was part of the temporary rigging used to balance the new section. When it failed, the platform shifted violently, shearing the support pins and causing the section to become a free-falling mass. It wasn't the crane mast itself that failed under load, but the temporary jacking equipment used to facilitate the growth. When we analyze the machine specifications of these jacking frames, we see they are engineered to handle the vertical weight of the entire upper crane assembly, which can exceed several hundred metric tons. However, they are significantly less robust when subjected to lateral or side-loading forces. When the cable snapped, it introduced a dynamic lateral load that the jacking frame was never designed to arrest. This turned a controlled engineering procedure into a gravity-driven catastrophe in less than 2 seconds. In a standard tower crane stepping operation, the balance of the counterjib and the main jib must be perfectly tuned so the center of gravity remains directly over the mast. This is managed by moving the crane's trolley to a specific radius, measured down to the millimeter. If the balance is off by even 1%, the hydraulic jacks in the climbing frame will experience eccentric loading. This places massive lateral stress on the support pins, stress they are not designed to handle. In Fort Lauderdale, once that support cable snapped, the section likely tilted. This tilt transformed a vertical load into a diagonal force, acting as a massive steel pry bar against the climbing frame's locking mechanism. For the engineers in our audience, consider the torque generated by a 5 metric ton section falling 91 meters. The kinetic energy upon impact is equivalent to a high-speed collision with a freight train. When a component fails in this disconnected state, there is no backup. There is only the acceleration of gravity. If the balance is the only thing keeping the crane vertical during a jump, then the rigging used to maintain that balance must be absolute. We often assume that because a crane is made of heavy steel, it is indestructible, but during a jump, it is at its most fragile. It is a game of millimeters where the weight of a single rigger shifting his position can theoretically alter the hydraulic pressures within the jacking cylinders. When you combine that sensitivity with a snapped support cable, you have a recipe for total structural collapse. This is why the precision of the jacking frame is non-negotiable. Once it deviates from the vertical axis, the entire system becomes unstable. When a crane fails in the heart of a city, it isn't just a construction accident. It's a massive economic shockwave. These machines are the heartbeat of the global real estate market. In Florida alone, the construction industry contributes over $100 billion to the state's gross domestic product. When a bridge is shut down and a project of this scale is frozen, the local economy bleeds. Consider the global perspective. In cities like London, Dubai, and New York, hundreds of jumps occur every week. Each one is a controlled risk. If the insurance industry begins to see these maneuvers as high hazard rather than routine, the cost of building upward could become prohibitive. We are seeing a shift where the cost of liability is beginning to outpace the cost of the steel itself. Are we prioritizing speed and density over the fundamental safety of the urban environment? The Southeast 3rd Avenue Bridge is a critical artery for Fort Lauderdale. Its closure didn't just affect the construction site, it affected thousands of businesses and commuters, creating a secondary economic loss that is rarely calculated in the initial disaster reports. This incident forces us to look at the hidden costs of urban development, the price we pay for living and working in the shadow of these giants. As skyline density increases, the safety buffer between industrial work and public life is shrinking, and that has massive legal and insurance implications for the next decade of high-rise development. The financial fallout of the Fort Lauderdale collapse is a staggering lesson in risk management. To reach a potentially over $100 million valuation, we have to look at the total cost far beyond the immediate twisted steel on the bridge. The most visible drain on capital is the infrastructure and property damage. The crane section punched a large hole through the bridge deck, and repairing reinforced concrete over a navigable waterway requires specialized marine engineering and round-the-clock labor that quickly runs into millions of dollars. But look at historical precedents to see where this is going. The 2019 crane collapse in Seattle resulted in a jury award of $150 million in damages. Then you have the massive burden of legal liability. A single lawsuit from a victim in the crushed Tesla is already seeking $50 million, citing life-altering brain and spinal injuries. That is only the beginning. The wrongful death claims for Jorge De La Torre could lead to settlements that often reach into the tens of millions in high-profile industrial negligence cases. Beyond the courtrooms, you have to factor in the crushing cost of project delays. In high-rise construction, every day a project is halted by a stop work order can cost between $50,000 and $100,000 in interest, labor retention, and lost revenue. When you add the direct loss of the assets themselves, a high-end tower crane and its specialized climbing frame represent an investment of several $1,000,000, plus the regulatory fines and the subsequent spike in insurance rates. The $100 million mark is a calculated, terrifying reality of modern industrial failure. There is a deeper technical question we must address. Was the rigging insufficient, or was the maintenance of that rigging the true failure? When a cable snaps, it is usually the result of one of three things: overloading, improper installation, or internal corrosion. In the Fort Lauderdale case, evidence suggests a combination of neglectful factors. Rigging for a crane jump is not like standard site rigging. It requires a level of precision that many third-party contractors may not fully grasp. If the cable was shock-loaded, meaning it was suddenly jerked by a shift in the crane's balance, it could have reached its breaking point instantly. But why was it able to reach that point? If the cable had been properly inspected for bird caging or broken strands, it likely would have been pulled from service long before the jump began. This highlights a crisis in the industry where the speed of construction is outstripping the speed of inspection. We're using 21st century machines with outdated maintenance mindsets, and the results are consistently fatal. The climbing frame is a complex hydraulic tool, but it is often treated as a simple steel bracket. Without rigorous, documented maintenance of every wire rope and every hydraulic seal, we are essentially gambling with every foot of height we add to a building. The OSHA investigation eventually pointed to a systemic failure in maintenance. Specifically, investigators cited the presence of significantly corroded and cracked support pins and bolts within the climbing system, along with improperly applied end connections on the wire ropes. This is the mundane, slow-acting reality of rust that led to a high-speed tragedy. In coastal environments like South Florida, the salt-heavy, humid air accelerates corrosion and metal fatigue compared to inland projects. The climbing frame components were neglected. There was a documented lack of qualified inspections. This highlights a critical lesson. In heavy machinery, there is no such thing as a minor inspection. This collapse wasn't an act of God. It was a predictable outcome of skipped inspections and ignored rust. The bridge has been patched, but for the industry, the hole left by this incident remains wide open. We must demand better, or we will continue to pay for our skylines with the lives of those who build them. Thanks for watching Hard Hat Industries, your source for serious machines doing real work. If you like this, hit like, subscribe, and turn on notifications so you don't miss what's next. Until then, keep your head down and your gear running.